We can formalize the possibility of heterogeneous coefficient by a heterogeneous model where each state S has its own coefficient beta S, which describes the effect of insurance on expenditure in that state. So the only difference between the heterogeneous model and the linear model from the previous part of this video is the heterogeneous coefficient beta S. Here is an example for when this heterogeneous model is plausible. A state with a less healthy uninsured population may see expenditure rise more in response to a given expansion in insurance. This can be because less healthy insurees would require more expensive care to get healthy. Suppose further that the uninsured population is less healthy in states with greater insurance penetration prior to Medicare. This can be due to adverse selection, so only the least healthy elderly remain uninsured. In this case, beta S will tend to be positively related to X as 0. But we're still maintaining that the error term is unrelated to the fraction of elderly with healthy insurance as before. So absent changes in insurance rate, all states would follow identical average trends in expenditure over time, or more commonly known as the common trends assumption. We can still use the two fixed effects estimator, and it's a valid question, how reasonable would this estimator be, since the two fixed effects estimator is based on the assumption that all states have the same coefficient. A single estimator by construction cannot be centered around each of the 50 different true coefficients in a heterogeneous model, but maybe the single estimator is still centered around the average of the true coefficients. If that's the case, then two fixed effects estimator beta hat might still be a convenient way to estimate the effect of insurance on expenditure in a typical state. Motivated by this, there is an active research area that investigates the expected value of the two fixed effects estimator when we allow for heterogeneous coefficients. For our paper, we focus on deriving the expected value of the two fixed effects estimator for our Medicare example. So this claim says that the expected value of the two fixed effects estimator can be written as the ratio of the covariance between the effect of Medicare on expenditure, the effect of Medicare on insurance coverage, normalized by the variance of insurance coverage increased due to Medicare across states. This weighting scheme for beta S is not obvious that the expected value would coincide with the average of beta S. But if this expected value is still close to the average, then we might still think that the two fixed effects estimator would provide a reasonable summary for the heterogeneous coefficients beta S. And in certain situations, this estimator would indeed be centered around the average. One such situation is where beta S is unrelated to the insurance coverage change. In this case, we prove that beta hat is centered around an average of the coefficients and therefore might still be considered an appealing estimator. However, the situation where the coefficients beta S is unrelated to the insurance coverage change is somewhat special. In a more general situation where beta S and X as 0 can be correlated, as we discussed earlier, this correlation can cause the two fixed effects estimator to behave rather poorly in the sense that its expected value is no longer close to the effect of a typical state. We prepared a concrete numerical example to illustrate such behavior. In this numerical example, we let the coefficient beta S to depend linearly on the insurance coverage prior to Medicare. So here, lambda is a parameter that governs how the state level coefficient beta S is related to the fraction of elderly with insurance before Medicare. When lambda is 0, the coefficient beta S is equal to 1 in all states, regardless of the prior insurance penetration, and this corresponds to the homogeneous linear model from the first part of this video. When lambda is less than 0, this is the heterogeneous model we discussed earlier, where states with a greater insurance penetration prior to Medicare have a larger coefficient beta s. We specify the fraction of the elderly with insurance before Medicare in a way such that the average value is always 0.5. And this way, no matter what the value of lambda is, the average value of beta s is always 1. And by varying lambda, we can vary the relationship between beta s and x as 0 while holding constant the average value. Under this numerical example, we can plot the range of the true coefficients as shown in the blue region. And on the horizontal axis, we have lambda, which governs the amount of heterogeneity in the coefficients. So larger lambda is, the wider the shaded region is. But no matter what the value of lambda is, the average value is always 1. We can also use the formula derived earlier in the claim to calculate the expected value of the two-way fixed flux estimator, and that's plotted in this black solid line. It's surprising in the sense that this line will not pass the average of the coefficients unless lambda is equal to 0. What's concerning is that when lambda is less than 0, the two-way fixed flux estimator would on average underestimate the coefficient for all states. And when lambda is greater than 0, it would overestimate the effect on average. That means when lambda is not 0, not only are you not estimating the average effect across all states, you're estimating something that's lower or higher than the true effect in every state, depending on the sign of lambda. To understand why the two-way fixed flux estimator behaves this way, let's focus on the case when lambda is positive, which means states with a larger increase in insurance coverage would have a larger coefficient beta s. So the impact of insurance on healthcare expenditure is also larger. Then, following Medicare's introduction, expenditure grows more in states with a large increase in insurance coverage, both because of the large increase in insurance coverage and a large change in expenditure for a given change in insurance coverage. As a concrete example, let us revisit the numerical example with lambda equals to 1, but focus on the situation where the sample only includes two states, state 1 and state 50. Here, state 1 experiences a larger increase in insurance coverage due to Medicare, but also a larger change in expenditure for a given change in insurance coverage, visualized as a steeper slope than state 50. The two-way fixed flux estimator, however, is based on the assumption that the slopes are the same for these two states. So to estimate the average slope, it tries to back out the slope by only adjusting for the difference in exposure of the two states. And in the paper, we show that it will have an expected value that corresponds to the slope of the line that traces the overall impact of Medicare on expenditure across two states. Therefore, two-way fixed flux estimator is unable to separate the impact of larger exposure and the impact of larger coefficients, and will tend to overstate the effect of insurance on expenditure alone. In this numerical example, this conflation is so severe that the expected value of two-way fixed flux estimator, the slope, which is slope of the solid line, would fall outside the range of the true coefficients, which is the slope of these two individual lines. This is an example where there is no state that's totally unaffected by Medicare. And in this situation, next, I will show you that the issue we've seen with the two-way fixed flux estimator would apply more broadly to other estimators as well.